Hello, my name is Sanjoy Baruah. I work at Washington University in St. Louis. This is work I did with my frequent collaborator, Professor Alan Burns at the University of York, and with Yue Wu. She is an undergraduate student at Washington University. So I want to talk to you here about IDK-Cascades. But in order to do so, I must first talk about binary classifiers. A binary classifier is a software component that accepts input and determines whether this input does or does not belong to some class, to some category. You might, for instance, have a classifier for identifying cats. This would presumably accept as input images, photographs, and determine whether this photograph includes an image of a cat or not. Problems solved by such classifiers are often imprecise and poorly specified or defined. There is, to my knowledge, no mathematical model or definition of what does and does not constitute a cat. The results obtained by such classifiers for imprecise problems tend to be associated with a certain level of confidence. How confident is the classifier that the outcome it's generated, the result it computed, is the correct one or not? It has been proposed that when the confidence a classifier has in its outcome falls below some pre-specified threshold, it is more appropriate for the classifier to output a third value, an I don't know or IDK, rather than output a result on which it has no confidence. Such IDK classifiers can therefore be characterized by a bunch of parameters. There is an execution duration, which is essentially what we refer to as the worst case execution time of the software that implements the classifier. A classifier that might output an IDK could also be characterized with a success probability. This is a reflection of likelihood that this particular classifier will respond with an IDK rather than a yes or a no. This success probability parameter is generally obtained by extensive testing of the classifier once it has been constructed, trained, and is ready for use. The hope during such testing and profiling, of course, is that the data that is used for such testing, for such profiling, is representative of the kinds of data that the classifier will encounter on actual executions during runtime. The notion of using such IDK classifiers to construct what are called IDK-Cascades was presented first at a paper just a few years ago by Wang and his colleagues. The idea was this: we could construct multiple IDK classifiers for the same classification problem. These different classifiers would differ from one another in their execution duration and the probability that they would obtain correct answers. Let us, for example, suppose that we have two classifiers for the same classification problem. The classifier C1 has an execution duration of 6 time units and returns a correct answer 40% of the time. Classifier C2 has a greater execution duration of 10 time units, but returns the correct answer 75% of the time. An IDK cascade would be constructed by executing C1 on some input, and only if this classifier returns an IDK would we call the classifier C2. To quote from the paper by Wang and his colleagues, the idea is to combine IDK classifiers of increasing accuracy and computational cost. In our case, computational cost corresponds to execution duration, such that each will either render a high accuracy prediction, a yes or a no, with a high level of confidence, or would respond with an IDK, in which case we would pass the input on to the next classifier in the cascade, which is more likely to give us a correct prediction, it is more accurate, but the execution duration is greater. With regards to our example, on any given input, we would first call the classifier C1. If this responds with a yes or a no, we are done. Otherwise, it responds with an IDK, and we call the classifier C2. There is no reason why we have to stop here. We might have a third classifier C3 for this problem that has an even greater execution duration of 20. However, it always returns a yes or a no answer. Its probability of doing so is 1.0. In that case, if the classifier C2 responds with a yes or a no, we are done. Otherwise, it responds with an IDK, and we will call the classifier C3. Let us trace the execution of this particular cascade of IDK classifiers on some input. When receiving the input, we would call the classifier C1. If C1 returns an IDK, we would call the classifier C2. And if both C1 and C2 were to return IDK, we would call the classifier C3. Since C1 is always called, it has an execution duration of 6. C2 is only called when C1 fails. This happens with probability 1 minus 0.40. When this happens, the execution duration is 10. The expected execution duration for the classifier C2 is therefore given by this expression. Similarly, C3 is called only when both C1 and C2 fail. When it is called, its execution duration is 20. Its expected execution duration is therefore given by this expression. If you do the math, you will observe that these durations sum to 15, which is of course less than the execution duration of the deterministic classifier, the third one that has success probability 1.0. So this was the idea behind IDK cascades. By using less accurate but faster classifiers earlier in the cascade, we could reduce the expected duration of obtaining non-IDK answers than if we were to only use a deterministic classifier, one that gave us a correct answer with probability 1.0. Returning to the quote in the original paper by Wang and his colleagues, observe that they had suggested we cascade the classifiers in order of increasing accuracy, the DI parameter, and computational cost, the DI parameters. And this is indeed what we have done in our example. BI and DI are all least for C1, most for C3, and intermediate for C2. But it turns out that there is no reason why we have to follow the order of monotonically increasing BIs and DIs. To see why, let's revisit our example, and suppose we were to swap the roles of C1 and C2 and call the classifier C2 first, and only if C2 returns IDK should we call classifier C1. One given input, therefore, we would always call C2. If C2 fails, that is, it returns IDK, we would call C1. And if both C1 and C2 had failed, we would have called C3. The execution duration of C2 is therefore always 10. That the expected execution of duration of C1 is its actual execution duration 6 times the probability that it will be executed. Similarly, the expected execution duration of C3 is its actual execution duration times the probability that it will be executed. If you do the sums, you will observe that the expected execution duration for this cascade is 14.5, which is of course smaller than the 15 we had seen earlier. This cascade is therefore superior to the one we had seen earlier and serves as a counterexample to the conjecture that the right thing to do is to arrange the classifiers in the cascade in order of increasing success probabilities and execution duration. Let me now briefly enumerate the problems that we have considered in our paper that appears in the proceedings. We assume that we are given a collection of IDK classifiers, all for solving the same binary classification problem, that are characterized by different execution duration and success probability parameters. Given such specifications, our objective is to determine the order in which all or some of these classifiers should be arranged in a cascade in order to minimize the expected execution duration. With regards to our example, we have seen that the second cascade, C2 followed by C1 followed by C3, has a lower expected execution duration than the first cascade. It turns out that this second cascade of C2, C1, C3 is in fact optimal for this particular problem. In our paper, we have also considered an extension to this original problem. We assume that we are in addition given a maximum duration within which all computations must cease, even in low probability circumstances. Returning to our example, suppose such an specified end-to-end duration of 30 were known. Since our three classifiers, if all were to execute, would have execution duration of 6 plus 10 plus 30 or 36, we cannot include all three of them in a cascade. We must include the classifier C3 since it is the only one that guarantees to return a yes or a no answer. We therefore have a choice of two cascades, C1 followed by C3 or C2 followed by C3. If C1 were to be followed by C3, this is what the expected duration would be. C1 always executes, C3 executes only in the event of C1 failing. If we were to execute C2 followed by C3, this is the expected execution duration. We would always execute C2 and we would execute C3 only if C2 fails. Since 15 is smaller than 18, we conclude that the optimal IDK cascade, given a specified maximum end-to-end duration of 30, is the cascade C2 followed by C3. Let me now briefly enumerate the results we have obtained towards solving this problem. Further details about these results you can find in our paper that appears in the proceedings. We first considered the version of the problem when there is no maximum end-to-end deadline specified within which the entire cascade must always complete execution. For this version of the problem, we were able to obtain a very efficient algorithm that solves the problem optimally in big O of n log n time, where n is the number of different IDK classifiers that are available to us. We next considered the case where this maximum end-to-end deadline D is specified, and it is required that under all circumstances, including unlikely ones, the execution of the cascade complete within an interval of duration V. This problem turned out to be, from a computational perspective, less tractable than our previous problem. And we were able to obtain an optimal algorithm, but this algorithm has pseudo-polynomial running time. Finally, let me attempt to provide some context by explaining the various parts of this formal model of IDK cascades that we have put forth here, and trying to explain our results within the context of this model and its justification. We propose that the maximum duration, the end-to-end deadline, be considered to be some kind of safety constraint. It is required under all circumstances, including unlikely ones, that the result of the classification be obtained within this specified duration. In contrast, we look upon the expected duration as a performance metric that is to be optimized, in this case, minimized. We would like to be able to perform our classifications as rapidly as possible. Our recommended implementation practice, should the computing resources be available to you to do so, is as follows. We recommend that you synthesize an IDK cascade optimally using our first algorithm, ignoring the specified maximum duration. This part of your design is focused upon optimizing for performance. Separately, on a different processor, we recommend that you execute a deterministic classifier, one that guarantees to classify the input, not output in IDK. So the idea here is that we are separating considerations of safety from considerations of performance. We are ensuring that we are guaranteed to complete within the duration of the deterministic classifier, and hopefully this will meet the safety constraint. If not, the system is infeasible. The other processor, the one in which the IDK cascade that we have synthesized is executing, is focused on optimizing for performance only. It is not related to the safety of the device. The benefit of this approach, of course, comes from the fact that we are separating considerations of safety from considerations of performance. It allows us to focus our safety verification and certification efforts upon the deterministic classifier only, without worrying too much about the IDK classifiers. For instance, now it's no longer the case that the parameters of the IDK classifier in particular, the success probability of the IDK classifier. Be subject to verification at safety cognizant levels of criticality, because this parameter is only concerned with optimizing performance, not ensuring. So that's pretty much all I had to say here. We looked upon IDK cascades as a very interesting idea from the domain of machine learning, and made an effort in this work to subject this concept, this idea, to analysis using the techniques, tools, and methodologies of real-time scheduling theory.